Ladies and gentlemen, welcome to our latest STARS tutorial on AI in safety critical railway applications, validation and homologation. It will be performed by Fraunhofer Institute Focus, and our speaker will for sure say some words about the institutes in some short words. My name is Lutz Hübner from Berlin Partner for Business and Technology. We are one of the partners of the STARS project, and with this tutorial, we are opening a so-called European Week of Advanced Technologies for Railway Applications, where this is an umbrella for certain events which will take place from today until the 14th of September. The first point are virtual business meetings with our on our platform, B2B matchmaking platform. The second element are the STARS tutorials. We have several tutorials there. And the third one is the STARS Hack and Match event number five, which will take place tomorrow and on Friday. On Friday, yes. So coming back to the first element, this is the STARS B2B matchmaking platform, where virtual meetings are possible between the partners. The only precondition is that you set up a short profile on you and your company, and then you have the possibility to ask other participants for a meeting. We have here dedicated meeting slots at this week. You will find this by visiting this website, but in general, it is possible to meet every time because it is a long-going website, and you have the chance to meet each other also at midnight or at Sunday, or if it is possible. The second, about the STARS project is to support small, medium-sized enterprises of the rail supply industry in successfully adopting advanced technologies to boost their products, services, manufacturing processes, and their organization. That means in the focus are small, medium-sized enterprises. We have 10 cluster organizations, 5 technology centers, 1 digital innovation hub, and 1 blockchain provider, and 30 supporting organizations as partners or supporting partners of this STARS project. Yeah, sorry. Next slide is slide number 5. That is here you see a list of 8 technology trends have been identified in a technological innovation analysis within the STARS project, which have major impact or might have a major impact to the future European rail system. And the challenge of the STARS project is how to tackle these innovation trends with the help of advanced technologies by small and medium-sized enterprises. In this cloud, you see some keywords on advanced technologies. There are in total 16 on the list, and one of it is also artificial intelligence. What is the topic of this tutorial today? Yeah, we want to start with the first with a presentation by Professor Dr. Schwingloff. He is Chief Scientist of the System Quality Center at the Fraunhofer Institute Focus, based in Berlin. And I would say the floor is yours.
Screen here. So this would work now, and now I start my presentation. Oops. Now you should see it. Okay, so thank you for the introduction. just said, I'm a chief scientist of the System Quality Center at Fraunhofer Focus. I'm located in Berlin. Critical railway applications. I will talk a little bit about validation and homologation issues which we encounter. In my talk, I will first comment why AI or deep learning is a new programming paradigm. Some examples of AI in railway systems, potential applications, and then how this could be for AI components. And then I will talk a little bit about validation approaches, which we give you a short overview about upcoming standards for certification. And by the way, many of the illustrations which I use, like this nice menu here, are by Microsoft or company. Why is AI a new programming paradigm? Well, I should be more specific what I in this talk, AI will refer to components comprised of artificial or deep neural networks, where we have heavily parameter-dependent
Mr. Schlingler?
homogeneous structures.
Yeah.
Yeah.
May I ask you to switch off your camera, please, because of the bandwidth of
My camera switching off.
yeah, because then we have a wider bandwidth to understand you quite better then.
Yeah,
Because
thank
the
you. I
connection is
have
not,
no
yeah,
idea
yeah.
how I come across. Refer to components of deep learning structures, which are heavily dependent on systems have about 10,000 to 100 billion parameters. This is the and compared to the human brain, which has 10 to 11 neurons, you see that we are in a, let's say at the moment. And so in order to program something like this, we need optimization. So it's no longer a traditional coding, but it's training. And when I was doing this, I was a bit surprised that they are more involved with data gathering than with the actual programming or the adjustment of the meta parameters, which is usually done by heuristics. Of the data in the development. And this is also reflected in an AI application as compared to usual applications. We have data acquisition, then the data then the meta parameters are set up, and then there comes the training process. After that is the into use and is deployed. So it's completely different from traditional V-style programming. Okay, so where is AI typically used? Well, for me, it's all techniques where computers mimic the groups, and so we can look at how or what humans learn. Well,
May I interrupt you? There
nice
might,
phases. So if you
Mr.
look,
Schlingloff, just
yeah,
an issue. You have every time some interruptions of your voice. Maybe you could use another microphone or do it with out external microphone.
the microphone then. I hope it's better, but you can tell me whether it improves or not.
Yeah, yeah.
So looking at what humans learn, well, the very first thing you learn at an age of, let's say, it's not working.
Yeah, and that are every time some interruptions in it as the connection is frozen then for the moment, and then you will continue. Cannot say what the real issue is for the moment.
Okay. So we could, I could try to. I'm in the institute to have a good at the moment. Let's see. One possibility would be that I switch the turn out to work.
Yeah. Second possibility could be that you dial in via telephone.
Yeah. This is what I'm trying to.
Mm-hmm.
To achieve right now. So switch here to.
Or to leave the meeting and then re-enter. There are several possibilities.
Hello.
Yeah.
Hello.
Yeah, I can hear you.
Okay, so now I'm connected via mobile phone. I'm circumventing our institute network, and I hope it's better.
Yeah, it's better.
Okay, thank you very much. I'm sorry about this, but it's something with the institute network here. Okay, I was beginning to tell about where machine learning is mimicking human learning, and the first thing you learn as a human at the age of 1 or 2 days is to recognize faces. So you would recognize this left as a face and the right consisting of the same elements as not a face. And also image recognition was one of the first things for AI to investigate. And then a human begins to walk on 2 legs, and this is pursued in AI, in mobile robotics, in humanoid robots walking on 2 legs. And then understanding spoken language or reading, writing a text. This is something which is recently very interesting for AI. You know, ChatGPT and other systems which can produce text, large language models, playing board games. Children learn in kindergarten, but also now we have, let's say, AlphaGo doing this quite decent, or operating, supervising complex machinery, maybe more difficult, driving or a train or car. This is something where we are talking about today, doing this by an AI, doing trade business or recognizing fraud might be even more complicated or complex. And these are things which are pursued in AI research. And then, of course, there is the collective or collaborative intelligence in a soccer situation, for example, where a group has to perform, or a business team or a social group has to do something. So this is done with collaborative machine learning. So this is area of research how to do this at the moment. So where can AI be used in railway? The first thing which you could think of, what does a driver do, is recognize obstacles within the vehicle clearance gauge. And this is, of course, the main use case in the KI lock project where I'm involved with, where it's dubbed KI lock for a driver's license for AI TCMS. And another research project which we do at the university is optical signal switch and track recognition. So you have a camera image and you recognize where the track is and which signals and switches are along the road. And the second use case of KI-log will be multi-sensory vehicle localization or virtual odometry. We just began to look at that. And another future application might be train-specific acceleration and deceleration. So if you have a tank wagon filled with fluid, then it might be not easy to avoid that this goes back and forth. But of course, you cannot only look at the track, but also at the train, but also around the track. So checking of train and load status. If you have a train on the track and you have a robot which inspects whether the sequence of cars is correct or whether the loads are really in order or fixed appropriately. So this could be done by an AI. Another project where I'm involved with is the IM4Rail project of the EU Shift to Rail initiative. So their use cases are inspection of the train, for example, underbody inspection, brakes inspection, or a mobile robot moving along the track and inspecting the tracks, the catenary, or the rails, whether they're in order. And of course, there's a huge area of predictive maintenance where the train and the tracks can be maintained. For example, it is possible. I talked to a company here in Berlin, which recognizes whether the switches need to be changed. They look at the voltage during a switch operation, and from this they can learn the remaining lifetime of the switch. And of course, there's a load of applications in supporting areas like timetabling. This is currently done by heuristics, but of course, if you need a quick adaptation, for example, if there's a fault on the tracks, then the timetable must be rescheduled, and it's hoped that this will be done by AI soon. And of course, the whole area of passenger information systems, there are loads of things which you could imagine, and also in educational training of personnel, in railway personnel, already now in driving simulators, there are AI components improving the training behavior. So many possible applications, but of course, some of these are safety critical, and we have obstacles about using AI. At least it's said that AI-based rail applications must be capable to reach SIL 2 or higher. And as we have seen, it's a completely different life cycle. So classical quality assurance and certification methods are largely not applicable. So the first thing you notice about artificial neural networks is that they are of a stochastic nature. So it's not that you have a definitive conclusion. You always have, let's say, a certain probability that the left thing is a dog and the right thing is a cat, but there's no absolute guarantee here. Why is this? Of course, this depends on the training data, and it is obvious that the behavior and the quality of the network is heavily dependent on the size and the quality of the training data as such. And moreover, it is often not possible to formally specify the intended function. If we look at cats and dogs, how would you formally specify what is a cat and what is a dog? And of course, there are even borderline pictures where even a human could not determine. And this becomes even more difficult if you train the data, you train the network on laboratory data, and then it's deployed. in the wild, and it might behave completely different. So there is a distributional shift, which is dependent on the change of environment. If the environment changes only slightly, the behavior can have a big change. And so a small change of the inputs can have massive effects. And this can even be brought about voluntary. For example, if you have such an image of a stop sign and you insert, let's say, small disturbances here, like black and white bars, then it could be that it is not a stop sign, but a go sign. So this is called an adversarial example. And if this is such adversarial examples are trained during the development phase, then backdoors can be introduced, so security can be compromised here. And if a neural network is deployed and then improved in the laboratory, then it can very well be that functions which it used to perform without faults become faulty, and this is called fateful forgetting. So comparable to old age in humans. And here's I looked at this study for illustration production here, and the manual says it has not explicitly been taught anything like who Frida Kahlo is, or what a llama looks like, or what a wide-angle lens does. It just studied 650 million images and captions and led to draw its own conclusion. That's why there can't be a regular manual based on functionality that the developers intentionally programmed in. Even the creators of DALL-E cannot be sure what DALL-E has or hasn't learned, or what it thinks different phrases means. Instead, we have to discover what DALL-E is capable of and how it reacts. And this is, of course, for safety engineers, a nightmare. If you cannot say what an application is doing, you have to discover it. So this is unacceptable for any safety critical deployment. So, but of course, there are things which can be done. For example, you might want to limit the deployment of the AI in a safety cage. So, like kids living in such a controlled environment, an AI behavior or a decision of an AI might be controlled and limited by a supervisor. And so the supervisor allows the AI to optimize the behavior only within a given range. And so this can be in different, we experimented with different architectures here. It can be predictive and adaptive, where you have specifications which adapt to the environment and so on. So there's a lot of research around this paradigm. You might also have something like a co-pilot, so an AI that continuously performs novelty detection during runtime, and it detects when an input does not resemble the training data, and then it discards this input. And so there are research approaches where information from the final layer of a deep neural network is used to detect what an outlier is. So it looks inside the black box of the net and looks at certain neurons, and these certain neurons tell us when something is going wrong. And of course, what we are also investigating is to use traditional methods from fault tolerance. So one might have not one, but like 3 different nets for a decision, and then look at the output of these 3 different nets, and then make a 2 out of 3 decision. So if 2 kids have learned to walk and 1 is still crawling, then the decision would be that walking is better than crawling. So there are methods with which to improve the reliability of these decisions done by an AI. But of course, we would like to have at least some guarantees or some validation results in order to bring this into practice. So what can be done? Well, we can do also during the development, we could use quality assurance and validation methods. So for example, we could evaluate the data sources and see whether they have a fair and balanced distribution, and whether the quality of the data is sufficient. Not only look at the quantity, but also at the quality of the data. We might also look at outlier detection and outlier handling. We might want to eliminate outliers. In other cases, it might even be better to generate outliers in order to have exceptional cases. So an outlier in an image recognition would be something which does not resemble something which could ever happen. For example, a train hovering above the track or so. But an outlier which we might want to introduce is something which is an extremely rare situation, but realistic to handle. And of course, we can even calculate the probability of outliers and then determine whether these are to be discarded or added. And of course, we might look at this, what I said, the heuristics of setting up the hyperparameters of a net. And we can develop methods to have here pruning or testing methods in order to compare models and model behavior and to be able to predict how the model will behave in the future with certain hyperparameters. And there are other techniques which are being investigated, like overfitting prevention or training verification, or user evaluation and comparing the user behavior with what the AI does and so on. In a paper, we described to have this on 3 levels: on the reactions level, on the rules level, and on the principles layer, where the reaction layer would be the low-level input-output behavior, where we can have a mathematical envelope of operation. On the rules layer, we have logical rules which govern the behavior of the AI, and we can check whether these rules are being satisfied. And on the principles layer, we have general principles and priorities which cover the unexpected or anticipatable, and their testing of rare and exceptional cases. Let me comment a bit closer that you see at least one formula in this talk about analytic validation methods. Verification of properties of an artificial neural network is a very hot topic in research at the moment. And the most common example which is researched is robustness, which says that similar inputs lead to similar results. And for image classification, this could be formulated as if you have one image P1, which is classified in class C1, and you have a slightly different image P2, then P2 will be also classified as the same C1. And here's an example from the usual MNIST data set of handwritten digits. So this is the handwritten digit 7. And we have now a variant of this which is slightly lighter background, and another variant where there's a disturbance, a dot on the top. And of course, we would like to verify that these two pictures are still classified as digit 7 and not as a 1 or a 3 or whatever. And so this could be formulated as a formula for all P1 and P2. If the classification of P1 is C1 and the difference between P1 and P2 is smaller than a threshold, then the classification of P2 is also C1, the same classification. But if you look at this formula, then you see that there are too many possibilities, because there are, of course, very many pictures of, let's say, size 700 times 300 or whatever, and pairs of this makes this quadratic, and so there are too many instances to check. So what one usually does is one fixes one instance and tries to find a counterexample which is similar but not classified the same. So I try to find whether there is a picture which is in the vicinity of this first picture and has the same classification. And this is usually done by the so-called satisfiability modular theories solving, where the AI model is encoded as a formula, and the query is also encoded as a formula. You see it above, how the query is encoded, and then we deploy the known techniques for its, for example, a ReLU network, and we get a counterexample if there exists a counterexample, or we get the proof that no counterexample exists, which means that all similar pictures are classified likewise, and so the network is robust for this particular input picture. And so this works for nets of up to, let's say, 1 million nodes at present. Here is here are some benchmarks. So there's an annual competition, VNN competition, verification of neural networks. And so they have, for example, a car image segmentation challenge where the pictures are 31 by 47 pixel, and the network is like 300,000 neurons, or a database index determination, 100,000 neurons, or predictive maintenance of aerospace equipment with 28,000 neurons, or a lunar lander sensor noise robustness, a very small network with only 500 neurons. And these can be completely analyzed, at least by the cutting end of today's research. And the use cases in the literature which can be found are from cross-track error of planes on a runway, which is kind of similar to a train on the track. And there are some counterexamples that could be found. Or object detection in airport, which is somewhat similar to obstacle detection in railway, and there the robustness could be shown. What we are at Fraunhofer Focus mainly doing is testing. So in contrast to traditional software, verification of neural networks is incomplete, as we have seen on the previous slide. But we can employ usual testing techniques to test the trained networks. And there, the question is, how do we generate test scenarios and test data? How do we determine suitable test coverage? And how do we determine whether a test has passed or failed? And what we do is we employ simulation-based test generation, where we have the possibility of generating border cases or unlikely or expensive scenarios like people on the track, which you would not want to test in real life. And so we do this by using VR pictures for image processing. So here you see a railway scene, and even though this looks like quite a realistic scene, it is completely artificially generated by our tool. And if we give this to the system under test, which is the image recognition, then this flags us certain things which are interesting, like persons or poles or catenary or whatever. And now we can test this in, let's say, changing the lighting, not in the morning, but using an afternoon setting, and see whether the people are still detected. Or we can introduce some fog in the picture and see whether it's still detected. And if we increase the level of fog, then we see that the people are still there, but the AI does not recognize them. And of course, this is particularly important for a moving target. So this is a train on the track approaching a station. And there are some people, but at this distance, the people are not recognized by our system under test. And if we approach, we can see now it has detected that there's a person on the track, and it can perform some actions. So how do we do this in our testing environment? We have a possibility to generate random tracks and landscapes, but we can also generate virtual tracks from map data and satellite images. So we have here a satellite image of a scene or a map data of a scene, and we can transform this, analyze this, and make a virtual scene, a virtual reality environment out of that. And this we can then zoom in and put a track and put people in and catenary and whatever. So this is the basic functionality. We have as well as artificial tracks as well as real tracks where we can test. And then we take the pictures in our environment and we can use generative AI, so image producing AI, to adapt and modify the images. So for example, we can put this in a, let's say, evening or a winter scenario, or maybe a desert or whatever. So we can have many different test cases. And so our test case generation is based on an ontology. We have an ontology what scenarios are realistic in the operational design domain, and we can adapt that. And I should also say that we can include other sensors as well. For example, we start with a scene, then we modify the constellations, make in some perturbations as test cases. We disturb or perturbate the environment and weather and time of day and so on. And all these paths are then different test cases. And if we find that the SUT fails under a certain test case, we can flag that and say, well, here the SUT did not recognize our ground truth. Of course, we do this for different scenarios. Each scenario gives rise to a whole bunch of test cases, so we can perform a very large number of tests very easily. And so we can gain some statistical evidence for certification. We can generate automatically expensive test reports for AI systems with a large number of test cases. I should say that this was a research of a research project, this KI-log project, and we even now founded a company, Paratrust AI, which is marketing this test environment. So if you're interested, then just talk to me and I will forward you. So here's an overview of the internals, how this test suite works. We have the scene description. We generate the virtual reality component. We export data, not only the image data, but also the data for determining the ground truth. Let's say where are the tracks and where are the people and so on. And we give this to the system under test and evaluate the performance. And this can be then fed back into the test generator, which can then adjust the scenes to see where the border of the capability of the AI lies. Okay, so this can be done for improving the quality, but is it enough for homologation? So there are some existing standards, but all of these are not relevant for really addressing neural network technologies. And of course, if you look at, let's say, European norm 5128, it talks about statement coverage, which is completely meaningless for an artificial neural network, or the life cycle is different, as I showed you, or the notion of requirements tracing may be inadequate. And even in this 5128, I found that artificial intelligence fault correction is not recommended. So certainly this is not a basis for homologation here. Let's look at other domains. In the automotive domain, which is strongly investigating the possibility of autonomous cars, there is, of course, this classical 26262 standard, which is comparable to our 5128. A couple of years ago, they came up with the SOTIF standard, safety of the intended functionality. So where it deals with performance limitations, complex environment, and human-machine interaction. This is kind of more more apt to this idea of AI and statistics. A few years ago, the first automotive standard for autonomous products came up, which is the ANSI UL 4600, which is mostly targeted at road vehicles. They also claim that they cover unmanned aerial vehicles. That they claim they are technology agnostic. So machine learning techniques are included amongst others, but this again has the obstacle that is, or the drawback that it's rather abstract. And so it suggests to have a robust combination of analysis, simulation, lab testing, and operational testing. And so this could be in rail applied for GOA 3 and 4, driverless and unattended train operations. But of course, let's see whether there are other things as well. Let's look at the aerospace domain. Classically, there is the DO 178C and its supplements. And again, if you look at it, this is inadequate for certifying AI systems. But at least the European aerospace industry is doing research here. And then most notably is an EASA concept paper, which is an upcoming standard for avionics AI systems, which is not finalized yet. So currently it's in the state only for human assistance and teaming systems, not for autonomous AI systems on the plane. But they also have a concept of design assurance for neural networks, where they give more details on the particular methods which are to be deployed. And here, if we take a closer look at this, the aim is to allow machine learning for onboard aircraft software in safety critical applications. So first of all, they defined a new life cycle for AI systems and design assurance of AI systems. And it has certain limitations, so it goes only for specific types of AI systems. But this concept paper definitely gives you about 100 concrete tasks or objectives, what shall be done for each assurance level and autonomy level. So this is here's a random example for a prescription. Would be the applicant should capture the requirements on data to be pre-processed and engineered for the inference model in development and for the operations. So this is something you have to do during the development of an AI system, which is to become airborne. So again, looking at the international community in the ISO is also researching this and drafting standards. The problem with ISO is there is a joint technical committee on artificial intelligence, and they currently are drafting around 50 standards. And 50 is quite a large number. So there are data quality for analytics and machine learning, functional safety and AI systems, controllability of automated artificial intelligence systems, verification, validation, analysis, and so on and so on. So 50 different standards. And for practice, this is, let's be honest, too much information, right? And since all these standards are to apply on all domains, they are very generic and do not give you concrete certification requirements and no measurable success criteria. So they are of, let's say, limited help. Okay, so the situation is that Fraunhofer also then proposed some guidelines for designing trustworthy AI. So there is a Fraunhofer AI assessment catalog, which covers the trustworthy development methods and the assessment of trustworthiness. And this is a paper of 150 pages or so very well accessible. It has 6 dimensions along which to assess an AI, namely fairness, autonomy and control, transparency, reliability, safety, security, and data protection. And along each of these dimensions, there are 4 steps to be taken. namely first a risk analysis, then a definition of targets, then a listing of the measures which are to be taken, and then an argumentation why this is sufficient. And what is very valuable for is a particular homologation is that we try to quantify all the targets. So Fraunhofer guidelines give you concrete guidelines on how to design and how to assess trustworthy AI. So how can we help you here in this process? We do safety assessment of AI software on a routine basis. We have this in-the-loop testing approach, which I presented, of software with AI components. Specific the service here would be the environment modeling and the automated test generation, but we also deal with data preparation for machine learning and robustness analysis with respect to adversarial examples, and setup and tuning of meta parameters I talked about. So in general, we offer certification, support, and training and consulting in these methods. So this brings me to the end. My conclusion, what did I tell you about? I mentioned that AI components in railway applications have a great potential, but that traditional quality assurance methods are largely inadequate, and that this currently inhibits the deployment for safety critical tasks in mostly all domains. But on the positive side, I told you that there are constructive methods which increase the trustworthiness, and that there are even methods which you can employ during the development, that the verification of neural networks is still in its infancy, but it's rapidly progressing. So in a few years, we may be able to completely validate such a net. And currently, what we can do is we can do simulation-based testing. So these tools are becoming available, and they are even becoming available on the market, so you can buy them. Unfortunately, there is no railway-specific AI homologation procedure. I just came before this talk. I came from a meeting with a Deutsches Schienenforschungszentrum, which is connected to EBA, and so there is ongoing work. So there may be, let's say, in a few years, there may be specific standards for railway. But my impression is that other domains are advancing more quicker, and that there should be done more in the railway domain also to improve this. So this ends my talk. Thank you for your attention.
Yeah, thank you very much, Holger, for your impressive presentation. The sound improved, and hope that this was good for sure. And yes, the first thing is to ask you whether there are some questions. I didn't saw questions from the chat, but there is a hand sign. Maybe you could unmute yourself and raise your question.
Yeah, maybe I will go first. I hope you can understand me well.
Yeah,
So
Daniel
thanks.
Kanzler, the first one. Yes.
Thank you. Thank you very much for that really impressive presentation. What I realized that I also wrote it in the chat, there is, for example, right now also an ongoing project about defects in rail detection, a topic which is right now very hot. And what I realized is things you showed and this specific application of AI, they are so different that maybe we don't need to have like one specific standard for all AI in a railway, but that we really concentrate on the use and concentrate on the circumstances because on some specific things, for example, a person walking into the rail, there are some completely surrounding or different surroundings than when we are talking about specific cracks and specific physical understandings what is happening in the testing environment. What do you think?
Yeah, I think yes, definitely true. So one size fits all is rarely a good approach here. What current approaches in aerospace do, what I told you, is that they couple the load of verification to the grade of autonomy, and autonomy means what is the system allowed to decide on its own. And so if it's decided, if it, for example, has a decision on whether to go faster or slower, of course, this decision should not override what is given by the rules of the track. Yeah, and so yes, we need to couple the standards to the criticality and the criticality to the autonomy. Yeah, so this is like 3 dimensions here. Maybe it is, I can answer the question which is on the screen at the moment, because this is related, I think. The question is, how good is the detection of persons with the help of AI for the railway application with respect to longer braking distance? What I showed you today, these pictures are from our testing environment and from the SUT, which our partner, our industrial partner provided. And of course, you can adjust this by having, let's say, a long distance camera with a which looks ahead, or so then you could look longer ahead. But we also experimented, let's say, with people hiding or being obstructed by vegetation. So if somebody is standing behind a bush, well, then the AI, of course, doesn't see it, but maybe a train driver, a human train driver, wouldn't see them as well. So if somebody is hiding behind a bush and then jumping in front of the approaching train, no automated system will ever be able to avoid that. I mean, this is something where you have to balance what a machine can do and what a human can do. And of course, there is this principle also about the new system must be at least as secure as as safe as the old system. And if the old system is a human operated system, then we have to assess what is the capabilities of human in this range here.
Yeah. We have, thank you. We have 2 more questions, and one question comes from a person with a raised hand. Please unmute your micro and raise your question.
Hello.
Yeah, hello.
Thank you very much for your clear presentation. Just I have a question. Actually, I'm working on vegetation detection on railway using semantic segmentation. As I see in your presentation, till now you have only the synthetic data. You don't have real data to validate the model, yeah?
Yes. So for the training, real data was used from the RailSim set, but for the testing, we test currently with synthetic data. Yes.
Okay. Actually, I'm working on RealSim dataset also.
Okay.
And I have another question: if the synthetic data, if it's available to everyone, or it's confidential for your lab?
It is generated. What I said, it's generated by our tool from an ontology. So it's completely synthetic. It's generated. It's not a fixed set, but
Okay.
we have an ontology of where you specify what you want to test, and then the test data are generated automatically.
Okay. Thank you.
So we have two more questions, and these are the two last ones. And maybe Mr. Schlingloff will also leave his contact data in the chat so that you have the possibility also to reach him afterwards. But I could include the follow-up, the contact data also in my follow-up email within the next days. Question is, which are the domains from which the railways can learn quickly?
Yeah, as I said, so I think currently the aerospace domain is quite advanced. The automotive domain also has a lot of research ongoing, but they are not so willing to share. So I'm not I'm not aware of, could also be, but I'm not really aware of upcoming standards in the automotive domain. But so currently I would look at these two papers which are referenced here.
So last question, when is it expected to have a regulatory environment to allow to use and homologate AI for safety critical applications? Is any railway standard group working on it?
Yeah, that's a very, very good question. But as you know, the cycles in railway are quite long. I mentioned that I had a conference with Deutsche Schienenforschungszentrum, and yeah, there is, for example, an ongoing. They announced that there is a meeting on standardization of terminology of AI in rail. So that they fix the terminology, and this meeting is scheduled for next month. And so there will be an upcoming standard maybe next year where the terminology at least is fixed. And then I think up to that we have something comparable to, let's say, 61508 or a railway specific standard for AI might be 5 years or longer. I have no idea.
Yeah. Thank you very much, and thank you for the presentations and all the answers. We will have 2 or 3 minutes delay because I will give you some additional information on the next STARS activities. Today was the start of the European Rails of the European Week for Advanced Technologies for Railway Applications. And first to say yes, there will be a recording of this event and maybe also a PDF presentation. You have to decide, Mr. Schlingloff, if it would be available. But the recording will be available in a few days at our STARS YouTube channel. Then, as mentioned, it was the first element of the European Week for Advanced Technologies for Railway Applications. The next element is, as I mentioned before, the B2B matchmaking platform where you can register and can meet with other participants. Then we have tomorrow and then the day after the Hack and Match event on advanced technologies for resilience of the railway supply chain. There will be a kick-off meeting tomorrow in the morning at 9 o'clock and a closure meeting on Friday at 5 p.m. And if you are interested in what challenges are going on in this Hack and Match event, please use the chance to click into this kick-off meeting. In order to give you an idea of what challenges we have, I prepared a slide with the challenges. There are 12 in total, especially small, medium-sized enterprises from different countries. And we have a Spanish company which seek an innovative AI or methods to accelerate manufacturing cost studies. We have Panto Health from Germany. They want to develop a real-time monitoring system for lifts and accelerators in rail stations. We have the Ghana Ministry of Railway Development, which is for sure not in small, medium-sized enterprises. It's also outside Europe, but we took it inside. They are looking for AI to make the most of the data collected from IoT sensors. Then we have Neurodec, which are exploring AI solutions to simplify the review and assessment. We have Weave, which going to create a simulation for testing braking resistors in order to develop a digital twin model. We have green buffers from not from Spain, but from Sweden. They want to achieve zero uncontrolled derailments in train collisions. We have Talgo from Spain. They seek an automated risk analysis system for railway vehicles. We have Lucchini, which is a well-known group based in Italy. They seek to reduce power demand in onboard train sensors. Then next slide, we have again Lucchini, which want AI to help extract sophisticated insights. We have photo laser manufacturing based in Berlin. They are looking for a digital twin for rail, car, body, in-white production. We have Zitsche. They are need expertise in railway line monitoring and diagnostics applications related to emissions and thermal losses in civil buildings. And we have MC Ledger, based in France. They aim to provide AI solutions for suggesting optimal routes. So, if maybe some topics are also interesting to you, and we have built 12 teams, and we have the challenge providers, these 12, we have also some solution providers, and they will discuss within the next 2 days on some approaches of a good solution. Then we have another STARS tutorial on EU funding for the railway sector, including a presentation, a first presentation of the upcoming call for exploratory research of the Euros Rail joint undertaking. It will be open in October. Then we will have some information, some useful information on the working program of Horizon Europe, and we will introduce to you a EU funding instrument called Digital Europe within this tutorial. We will have another tutorial performed by Fraunhofer, but not by Focus, but by IZM on smart sensors and communication technologies for railway applications next Wednesday, starting not at 11, but at 10:30. The colleagues need half an hour more. And for sure, you can also register to this tutorial. Then we will have another tutorial on the 14th of September from 11 to 12:30. It's the third part of 4 parts of the technology innovation analysis performed by our project partner Millennium, and it's on assets for automated or autonomous or remoted piloted operations on the one hand, and on the other hand, the topic of the network management, planning and control. We have interesting speakers from Millennium, from Alstom, and from the Gustav Eiffel University for this tutorial. And there will be a last tutorial within the STARS project, and it is the 4th part of the technology innovation analysis on regional rail services, innovative railway services for revitalizing capillary lines and railway multimodal and intermodal transport. The date is not yet fixed, but it will be in September. The SLAS project ends by the end of September, so this tutorial will be still in September. The date will be defined, and the registration link will be provided as soon as possible. So then we are in the end of this tutorial. Thank you very much for your attendance and have a nice day, and see you soon at one of the next STARS activities. Bye-bye.
Bye-bye.